Good morning, everyone. If you look in the meeting chat, I have a link for you to print out that 4.2 homework problems page. I think at the end we'll get a chance to work on some of the homework problems. Also, it'll be good for you to print out because some of the graphs, it's just easier to work directly on the sheets rather than having to draw out each of your graphs. So if you can either print that out if you get a chance or just follow along with that link.
Mr. Yang.
Yes.
So I was able to join the Teams through Remind, but there is no Teams on like my actual Teams app.
Right. So I know that I think it's a twofold issue. One issue is I think all the classes are getting dropped for some reason. I don't know if they've resolved it yet, but I know that's something that they're working on. And also for my class, I'm just not even going to create a Teams channel just because I don't foresee us being in virtual mode for very long. So I'm just going to be sending you a link every day.
Okay, sounds good. Thank you.
And I'll be choosing one of the recordings to upload to my website. So if you miss a class or if you get cut off, you'll always be able to find that link later in the day on my website. So I will be uploading each day's lessons to the website. So I think my hub is really the website, and Teams I'm just going to be using intermittently, hopefully, for these next few days, or if there's any random days that we weren't going to be using. So I'm not going to be using any Teams channel for our class. Okay. Let's start off with one of the homework problems from yesterday. This is a problem that a student from first period was asking about. So I want to just spend the time to go over it with you as well. So this is number 19 from the homework. Let me just kind of go over this problem. It says the summation from 1 to 15 of I times I minus 1 squared. So the first thing that we really want to do is make sure that we're not jumping directly to our summation formulas, because I know you see I squared, I know you see I, but right now the parentheses is making it kind of muddy. We really are not seeing the clear picture of the relationship between the summation formulas. So we need to spend the time to expand this out. Now, when you expand this out, make sure that you're expanding in the correct order. You can't just distribute the I through, because order of operation tells us that we have to resolve the parentheses before we can work in any multiplication. So we got to FOIL this out. And when we FOIL this out, we don't want to just distribute that square through and make it I squared plus 1. There's more to it than that, right? So you want to spend the time to FOIL. So write this out twice, spend the time to write it out twice so you can distribute each of the terms through. We get I squared minus I plus 1. Combine those middle terms, we get I squared minus 2I plus 1. Distribute the I through, and we get okay. So once you FOIL that I minus 1 squared out, then you can distribute the I through. Okay, now it's ready for that I. Distribute that I through. We get I cubed minus 3I plus I. Now that you have your cleaned up version of your expression with no parentheses getting in the way, now we can attach the summation to each of these terms. Okay, so we'll do summation I cubed. We'll do summation 2I squared, but along the way, I know that the 2 is not going to be impacted by the rule, so I'm just going to push that 2 out in front and isolate that I squared that I want to use my rule for, plus summation I. Okay, so now we have portions that are going to be used or replaced with the rule. So if you look on the first page of notes, I have those summation formulas written out. Summation I cubed will be n squared times n plus 1 squared over 4. Summation I squared will be n times n plus 1 times 2n plus 1 over 6. And summation I will just be n times n plus 1 over 2. I drag that 2 out in front. That's just going to tag along to whatever our sum is. We're going to now replace every n value with the upper bound. So upper bound of 15 will get inserted for all the n values. Right, and again, I'm just using these formulas that we walked through yesterday, right? So summation I cubed, summation I squared, and summation I. Okay, so insert 15 in for all the n's, so 15 squared times 16 squared over 4, 15 times 16 times 31 over 6, 15 times 16 over 2. Use your calculator to combine those values and we get 12,040. Okay, any questions here?
Mr. Yang?
Yes.
Can you do number 3?
Yeah, let me look at that. Yeah, number 3, you're not going to have any choice but to do it by hand. There's no rule that we can follow with number 3. So if it doesn't fit perfectly with our summation rule, sorry, k equals 0. I know you're looking at that k squared and you want to apply the rule, but it just doesn't fit, right? Because unless k squared is in the numerator, so if you're, if a rule can't be applied, and if you see it on the quiz, it'll definitely be one where you can do it by hand. It'll only be a few terms, if that makes sense. So if you can't use a rule on a problem, then it'll usually be small enough where you can do it by hand and it won't be too tedious. So plug 0 in first, then move on to 1, then move on to 2, and then your final k value is going to be 4. That's going to be the last k value that you use.
Mr. Yang.
Okay, to answer your question.
So when using n for all the summation rules, is that just going to be the difference between the upper bound and the lower bound?
Can you give me an example? I'm not exactly sure of your question.
So sometimes it says like I equals 1, and then like the top will be 5, and you use like the upper bound will be 5, and when you're plugging in for n, you use 5. But what if like it's like I equals 2?
Oh, good. Yeah, good question. If it's a problem involving summation formulas, it's always going to give to you in terms of 1. Okay. Yeah. So if it starts at 2, then we'll have to do some algebraic manipulation to get it to 1, but I won't give you ones like that. If it's a problem involving summation formulas, it'll always start at 1.
Okay.
Sorry, I need to let a student in here. Give me a second. All right, so let's start. Let's continue with the notes for today. Okay, today we're focusing on topic Riemann sums. Before we get into this, though, I want to kind of connect what we did first semester with what we're trying to achieve second semester. Okay, so first semester was all about derivatives. Right, and derivatives is just a fancy word for slope. Now, if you think about what slope is, right, slope is just rate of change in y over change in x. steepness of a curve. Numerically, or formula-wise, it's change in y over change in x, right? If we do y2 minus y1 over x2 minus x1, we can always figure out the steepness of a point, of a line, right? Either it's a steep line, or 0, or negative, or a really gradual slope. Okay, but either way, we were working specifically with a curve that had an ever-changing slope, and the derivatives allows us to find an ever-changing slope of any point on a curve. Okay, once we know that function, we can find that derivative and use that derivative to find the slope. Okay, so it was all about derivatives first semester. Now, second semester, we're basically going to be undoing this process, right? We're undoing learning how to go backwards through this process. So we call this antiderivatives. Now, antiderivatives means that we're going to be undoing this process that we did, or that we learned. I just want to give you a big idea here. Is if you look at this change in y over change in x, the big operation here is division, right? Division. So how do we undo division? What process do we use to undo division? What's the inverse?
Multiplication.
Yeah, multiplication, right? If you think about multiplication, right? So instead of y2 minus y1 over x2 minus x1, if I want to undo this process, I'll use multiplication. So think about what multiplication looks like. It's x2 minus x1 times y2 minus y1, or y2 minus y1 times x2 minus x1. It really doesn't matter. But I'm going to write it as x2 minus x1 times y2 minus y1. Okay, so essentially we're going to be undoing the process this way, but there's going to be some application that that's going to come out of this. Think about what x2 minus x1 times y2 minus y1 is going to give you. x2 minus x1 is going to be some horizontal distance on the graph, right? y2 minus y1 is going to be some vertical distance on the graph, or of a region. So what happens what do we get if we multiply a horizontal distance by a vertical distance?
Area.
Area of a rectangle. Okay, and that's the big idea. The big idea is that as we go through this antiderivative process, yes, we're going to be undoing the derivative procedure, but along the way, we're also going to be able to use this process to help us find the area of specific regions. So first semester was all about figuring out how to determine the slope of an ever-changing curve. And if we do the inverse procedure, we're going to see multiplication come out of it, and that application-wise is going to help us find the area under the curve. I know right now this is just the area of a rectangle, but we're going to expand this concept, use rectangles to essentially add up a bunch of infinitely thin rectangles to find the area of a region. Okay, so that's the big idea. The big idea is that we're undoing the derivative process. We're calling it antiderivatives, but then along the way, we're going to be able to solve problems that's area related and even extend out to volume. Okay. But we're going to be moving in that direction, but today we're just going to be focusing on approximating a region using rectangles. And that approximation process or procedure is called Riemann sums. Okay, so we're going to use rectangles to estimate the area of a region, okay, and learn about the different ways that we can use rectangles. Now consider our graph, our function f of x equals x squared plus 1. Okay, so that's this curve shown here. Parabola that is centered on the y-axis, but has a y-intercept of 1. From -2 to 2. Okay, those are our boundaries. Okay, so let's say we're working with the shaded region and also above the x-axis. Let's say we're working with a shaded region, and But today, we're not concerned about what the actual area under this shaded region is. We're going to be basically using this region and finding different ways to approximate this region.
Mr. Yang,
Yes.
you're not sharing your screen.
Oh, I'm so sorry. I thought I was. Guys, am I showing my screen? I thought I was.
I can see it.
I can see it.
Sometimes to see the
Okay.
screen, you gotta leave the meeting and come back.
Yeah, come back in, and hopefully that will show for you.
All right.
Okay, but thanks for bringing that up, because sometimes I don't realize that I'm not sharing my screen. Okay. Hey, so we're going to be estimating the area of the shaded region using different approximation methods. So the first approximation method is using upper rectangles. So upper rectangles is where we're purposely overestimating the shaded region here. And so which means that we're going to be drawing rectangles that's going to purposely peak above the curve so that we're creating a higher than actual area. All right, so I'm just going to kind of lightly shade these 4 rectangles here. I know it's kind of grainy. So I have my first rectangle here, second rectangle, third rectangle, and fourth rectangle. Right. I'm going to go ahead and assign these or identify the values of these subintervals. So this is -2 to -1, 0, 1, and 2. Now, in order to ensure that we're creating overestimations, what we're going to do is within each subinterval, we're going to look at each of the endpoints within each subinterval, and we're going to connect them to the graph. And we're going to see which vertical line from these endpoints of each subinterval is going to touch the graph at a higher point. You see that -2 is going to reach the graph at a higher point than -1 is. So we're going to choose the -2 height. So from -2, you're going to extend all the way to the curve, highlight that point, and that point is going to represent the height of your first rectangle. So you're going to drag that height through the entire subinterval and draw your rectangle there. Okay. So this will ensure that our first subinterval is going to be an overapproximation, where we should see a portion of the rectangle that sits above the curve. Okay, now for the second subinterval, we'll do the same thing. You see at -1, it's going to extend to the graph at this point. At 0, it's going to extend to the graph at a lower point, but we're always going to choose the higher of the 2 choices. Okay, so higher of the 2 choices is -1. So from the x-axis, you're going to extend to where the graph or where the vertical line touches the graph, highlight that point, and then extend that height over for your second rectangle. Okay, again, the reason why we're doing this is because we're purposely trying to create higher rectangles. Okay. Between 0 and 1, we see f of 0 is touching the curve at a lower point than f of 1. So we want to choose f of 1 to guide and represent the height of the third rectangle. So from the x-axis, you're going to extend to the curve at 1, highlight that point, and then drag that height over. Okay, so that will be our third rectangle. Fourth rectangle, you see between 1 and 2, f of 1 is touching a lower point on the curve than f of 2. We want to choose the higher of the 2 points. So from the x-axis at 2, extend the graph all the way to the curve, highlight that point on the curve, and then extend the graph over. And if you look, every rectangle should have regions that are clearly above the curve. Okay, so now using these rectangles, we will be able to provide an overestimation of the area under the curve. Notice that one corner of each rectangle is directly on the graph, This ensures that the height of the rectangle is the same as the value of the function at the point where they connect. Okay, any questions there? Okay, so same subinterval, same curve, same boundaries, but now we're going to create an inscribed or lower or under approximations of this actual region. Okay, so again, first rectangle, second rectangle, third and fourth. Let me indicate the subinterval values. So again, we'll do the same thing. At each of the endpoints for each subinterval, we're going to connect to the graph, and we're going to see which point on the graph with vertical lines connected will produce the lower value. Okay, now we're after the lower value. So between f of -2 and f of -1, we see f of -1 is clearly at a lower point on the graph than f of -2. So we'll choose f of -1 to represent the height of the first rectangle. So we're going to extend that height over the full subinterval, and that's how you draw your first rectangle. Okay, second subinterval, between f of -1 and f of 0, we're going to choose a lower one. F of 0 is clearly lower on the curve than f of -1. So you're going to highlight f of 0 on the curve and then extend that height over the entire subinterval. Okay, between f of 0 and f of 1, you see f of 1 is higher than f of 0. We want to choose the lower point on the curve. So highlight that point and extend that height over the third subinterval. Okay. For the fourth subinterval, you are choosing between f of 1 and f of 2. F of 2 is sitting all the way up here. We want to choose the lower of the two, so we'll choose f of 1. So extend all the way to the curve, highlight that point, and extend that height over. So every rectangle should be clearly sitting below the curve. The gaps that we see are no longer above the curve, but the gaps that we see are now below the curve, which means that the area of this lower sum is going to be a smaller value than the area of this region. Okay, any questions conceptual wise here? All right, so now if you look at the third and fourth approximations, these are not so concerned about whether it's a lower or upper sum. These are more concerned about whether we're consistently using the left endpoint of each subinterval or the right endpoint of each subinterval. So typically what's going to happen is on the AP exam, you're going to see less of these two examples and more of these two. It's just something that's that we see over the years as left-handed and right-handed rectangles are used a lot more often and involved a lot more often on AP exams than these first two. Okay, so here we're not even going to worry about whether it's an over or under approximation. We just want to make sure that we draw our rectangles the same way or the correct way. So left-handed rectangles means that for each subinterval, we're just going to blindly choose the left endpoint for each subinterval. Okay, so -2, -1, 0, 1, and 2. Between -2 and -1, we see -2 is further to the left than -1, so we're just going to attach the height at -2 to the curve and let that guide the height of the full subinterval. Okay, between -1 and 0, -1 is further to the left, so at -1, attach to the curve, extend that height over. Okay, between 0 and 1, you'll choose 0, extend to the curve, extend that height over. Okay, between 1 and 2, you choose 1. Once you get that 1, drag that height over. Okay, and because we're not looking for lower or upper sum, some rectangles will sit above, some rectangles will sit below, but that's not our concern. Right-handed rectangles, just like the name indicates, we're going to choose the right endpoint of each subinterval. So between -2 and -1, you'll choose the right endpoint. The right endpoint is at -1, so connect f of -1 to the curve and let that be the height of your first rectangle. Okay. Between -1 and 0, you choose 0, let that be the height. Between 0 and 1, you choose 1, let that be the height. Between 1 and 2, choose 2, let that be the height. All right, questions? All right, let's look at some examples on the second page. Okay, so here's second page here. Example 1, use 4 rectangles to estimate the upper and lower sums for the area bounded by x equals 0. That's the y-axis. Y equals 0. That's the x-axis. X equals 2. That's the vertical line here. And y equals x squared plus 1. So the same curve as the first page, but we're just going to be looking at that first quadrant region. Okay, so now we're going to be creating our subintervals on our own. The way we do that is first we need to find the width of each rectangle. The width formula is b minus a over n. A is the left endpoint. Okay. B is the right endpoint, which is 2. N is the number of rectangles, which is 4. So every problem that's asking you to estimate upper and lower sums, the problem will always provide you with information for you to find the width. You're always going to be given information for you to identify the left endpoint, right endpoint, and also the number of subintervals to build. Okay, so I'm going to take this graph and I'm going to kind of zoom in a little bit and just go ahead and create the 4 subintervals. So I'm going to take that region and I'm going to kind of blow it up to this graph here. Okay, so here's my x squared plus 1. Left endpoint 0, right endpoint 2, with 4 subintervals. Okay, so first step, let's go ahead and find the width. Our a value is 0, our b value is 2, and our n value is 4. Number of rectangles is 4. So width is going to be b minus a over n, 2 minus 0 over 4, which is 2/4, which is 1/2. Okay, the next step that you take after you find the width is you're going to manually find the value of each subinterval. So from 0, you're going to add 1/2. 0 plus 1/2 is 1/2. So go ahead and identify that subinterval value. Plus 1/2, we get 1. Plus 1/2, we get 3/2. Plus 1/2, we get 2. All right, so here we clearly see our 4 subintervals. And for part A, for this first region, we're going to purposely create an upper sum. So we're going to be creating rectangles that's going to be sitting above the curve, at least portions of it. So we're always going to be choosing between our left and right endpoint of each subinterval. So between 0 and 1/2, we see 1/2 is clearly higher than f of 0. So 1/2, you're going to go to the point where it meets the curve, highlight that point, and then drag that height over. Second subinterval, between 1/2 and 1, we see 1 is clearly sitting at a higher point than 1/2. So highlight that point, draw from 1 to the height where it meets the curve, and extend that height over. Between 1 and 3/2, we see 3/2 is clearly at a higher point than 1. So draw a vertical line to that point on the curve and move that height over. Okay, between 3/2 and 2, 2 is sitting at a higher point. So we'll let that be the height of the fourth rectangle. It just so happens that because this graph is always increasing, it's also a right-handed rectangle, right? But it's just because the graph is rising. But we're not just randomly choosing the right endpoint. We're looking at each value and seeing which one is higher and choosing it from that perspective. Okay, it just so happens that because the graph is rising, it also looks like a right-handed rectangle. Okay, but we're not choosing the heights based off of that that scenario. Okay, so we're going to spend the time to find the area of each rectangle and total them up. Okay, to find the area of, or find the value of this upper sum, this over approximation. So area of rectangle is width times height. So I'm going to use uppercase S to represent, the fact that I'm finding an upper sum over approximation, and 4 to indicate that we're using 4 subintervals or 4 rectangles. All right, so first subinterval here has a width, first rectangle has a width of 1/2. And the height determined at f of 1/2. So f of x is x squared plus 1. I'm not going to find the height just yet. I want us to practice writing it in function notation. So the height at 1/2 would mean I plug in 1/2 into the function. We'll find the height a little bit later, but right now I want us to write it as f of 1/2. Okay, so that indicates that we know what to do. We're going to be entering 1/2 into the function to get that numeric value, and we'll later make that substitution with the next step. Okay, so width times height, this will represent the height of my first rectangle. I'm going to move next to my next rectangle. Width of my second rectangle is also 1/2. Height is now determined at 1, so f of 1 is going to represent the height of my second rectangle. Okay, third rectangle. They all have a width of 1/2. Height will be determined at f of 3/2 for the third rectangle, because that's the point that we've attached to the curve. And then the fourth rectangle, f of 2. All right, so if I want to resolve these function notation values, I'm going to enter 1/2 into each of the function one at a time. So I'll put that over here. F of 1/2 just means that I'm going to put 1/2 to 0.5 squared plus 1, or 1/2 squared plus 1, which gives me 1.25. I'm just going to go ahead and just find all the y values that I need. F of 1, which would be 1 squared plus 1. 2, f of 3/2. Okay, so one by one, I'm just evaluating these y values so that I can get a numeric value to be plugged in. Okay, so 1/2 times 1.25, width times height for each of these rectangles. Total those up using your calculator, and you're going to get 5.75. Okay, we know that this area, this approximation is going to be higher. 5.75 is going to be higher than the actual area of the shaded region. We don't have to know how accurate this is. We just have to know how to find it if they ask us to find it, or if the problem asks you to find it. Okay. Okay, next up, let's find lower sum. So now we're going to purposely create an area approximation that is lower than the actual area. So same shader region, same graph, same subinterval. But now we're purposely going to choose the lower of the two heights. So between 0 and 1/2, we'll choose f of 0. Between 1/2 and 1, we'll choose f of 1/2. Between 1 and 3/2, we'll choose f of 1. Between 3/2 and 2, we'll choose f of 3/2. Every rectangle is now sitting below the curve. There are gaps, but all the gaps are now below the curve rather than above the curve. Okay, so let's set up our what area would look like from a function notation standpoint. 1/2 times f of 0 is the area of my first rectangle. 1/2 times f of 1/2, 1/2 times f of 1, 1/2 times f of 3/2. Okay, the only value we can kind of recycle the values that we found from before, since we already found them. The only thing that we didn't find before was f of 4, right? So f of 0, my bad. F of 0, if I enter 0 into the function, I get 0 squared plus 1, which is 1. Total those together using your calculator, and you'll get 3.75. So we're expecting the lower sum to be producing a smaller area value than our circumscribed rectangles, and we do see that's the case, right? 3.75 is lower than 5.75 over approximation, under approximation. And we know the actual area is going to be somewhere between these two values. We don't know exactly where it is, but later on we're going to be using calculus to find the actual area of this region. But right now we're just practicing and understanding how to create these approximations. Okay, questions so far? Okay, let's look at one more topic here, and that is a midpoint approximation. So midpoint rule is similar to upper and lower sum in the sense that we are still using rectangles, but instead of using the left or right endpoint of each subinterval, we're going to purposely use the midpoint of each subinterval to calculate the rectangle's height. So here's example 2. I kind of worked the problem out halfway, but I'm going to start from scratch. It says estimate the area under the curve of 8 over x squared plus 1. That's this curve that you see here. From 2 to 6, use midpoint rule with 4 subintervals. Okay, I'm going to start from scratch here so you can kind of see each of the steps along the way. So here's our graph. 8 over x squared plus 1 is going to be a curve that's going to be kind of gently sloping down in the curved shape. And we're only going to go from 2 to 6, so I'm going to mark off 1, 2, 3, 4, 5, 6. Okay, within each subinterval, let's find the width. Or let's find the width first, and then we can create the subinterval. Okay, we know our width formula is b minus a over n. My a value is 2, my b value is 6, and my n value is 4. So b minus a over n, I get 6 minus 2 divided by 4. So 6 minus 2 is 4, 4 divided by 4 is 1. Once you find your width, you're going to start at the left endpoint, and you're going to increment by the width that you just found. So 2 plus 1 is 3, plus 1 is 4, plus 1 is 5, plus 1 is 6. Now we could stop here and just use these values if we want to use the left or right endpoint, or if we want to use inscribed or circumscribed rectangles, but we're going to use the midpoint of each subinterval. Okay. So what we're going to do is we're going to find the midpoint within each subinterval. So between 2 and 3, we can use 2.5. And once you identify 2.5, extend or draw a vertical line to the curve. And once it meets the curve, highlight that point and use that height to represent the height of your first rectangle. So you're going to extend that height to both sides until you reach 2 and 3, and then you're going to draw your rectangle that way. Okay, between 3 and 4, midpoint is 3.5, so highlight 3.5, extend to the curve, highlight that point where it meets the curve, and then create your height from that point. Between 4 and 5, we can choose 4.5. 4.5, extend the vertical line to the curve, highlight that point, and extend that height both ways so that you can fill your full subinterval. Between 5 and 6, choose 5.5, extend to the curve, highlight that point, and then make your height represented by that midpoint height. Now, just by looking at these rectangles, you can already maybe tell that we're getting a better approximation than if we were just doing left or right endpoint. And the reason why is because every rectangle has portions that sit above and below the curve. So it's just kind of automatically going to give us a better approximation because it's going to kind of balance out between the two values. It's still not accurate, but at least it's better than what we had before, right? Every rectangle has portions above and below, kind of has a way of kind of balancing out. Okay. Now, we don't know whether this is an over approximation or under approximation. Okay, that's not the point. The point is just understanding how to create these rectangles and also understanding the fact that midpoint rectangles are better approximations than left or right rectangles, assuming that you're using the same number of subintervals. Okay, obviously, if you have more subintervals, there'll be less gaps. Okay, but given that we have the same function and same subinterval, your midpoint approximation is going to be naturally just be better than your left or right rectangles. All right, so let's go ahead and see if we can find the area of these rectangles. Okay, so I'm going to use M to represent the fact that we're using 4 midpoint rectangles. Okay. We want to do width and height for each subinterval. So the width of my first rectangle has a width of 1. And the height is going to be determined at 2.5. So we'll say f of 2.5. Okay, we'll find that value later, but right now just understand that we are kind of setting each of the areas up, width times height. Okay, second rectangle, width is still 1. Right, we don't want to just use 0.5, right? We want to use find the width of the full rectangle, right? That full width is going to be 1. Height is going to be determined at 3.5, so we'll say f of 3.5. Next rectangle, width is 1, height is f of 4.5. Fourth rectangle, width of 1, height of f of 5.5. Okay, just to speed up the process here, if we want to find the actual heights, we'll enter 2.5 in for x. So the height of the first rectangle will be 8 over 2.5 squared plus 1. Okay, once you get that decimal value, put it in the space and then multiply by 1 to get the area. To get the height of the second rectangle, plug 3.5 in for x. To get the height of the third rectangle, plug 4.5 in for x. Fourth rectangle, 5.5 in for x. Okay, so once we find those specific height decimal values, we're going to enter them back into the height of the area formula, and then width times height, width times height, width times height. Now all the heights, all the widths are 1, so that's why the heights aren't changing once we put it into width times height form. And then just add up all the individual areas of these rectangles, and then we have 2.34, which will be our midpoint sum. Okay, I have a few minutes remaining. I know I may go a little bit over, so sorry about that. I just want to go over number 31 real quickly. So this is on that link that I sent you, or that I put in the message chat box. 31. I drew this out, or I copy pasted this twice, so we can kind of practice upper and lower sums for each of them. So I know that these regions are not kind of grainy, but we're going to extend from the actual problem is showing shaded region from 0 to 4. Okay, let's do upper sum first. So upper sum means that we want to find purposely create rectangles that's going to peak above the shaded region. So my first, second, third, and fourth subinterval. For each subinterval, I'm going to purposely choose the higher of the 2 points. So between f of 0 and f of 1, I'm going to choose f of 1. So from at 1, you're going to extend to the curve, highlight that point, and then drag your height over. Between 1 and 2, we see 2 is clearly a higher point than f of 1. So extend to the curve. At 2, highlight that point, drag over. Between 2 and 3, we see 3 is hitting a higher point, touching a higher point on the curve than 2 is. So f of 3 will be the height of the third rectangle. And then the fourth rectangle, we'll choose f of 4. Okay, from here, we'll just find the area. So uppercase S of 4, width times height. Now here, we can just look at the graph and tell. Here, it's nicely labeled, so we can find those heights pretty easily. Width is 1. Height is 3. Second rectangle, width is 1, height is 4. Third rectangle, width is 1, height is 4.5. Or at least that's the best estimation that we can make, right? We're just kind of approximating this. This is all we have, so we're just using that as our guide. And then last rectangle, 1 times 5, height of 5. Okay, upper sum is going to end up being 16.5. Okay, so now let's try lower sum. Okay, lower sum within each subinterval. Now we're going to purposely choose the height that is lower between the two subintervals. So between 0 and 1, we see 0 is lower than 1, so we'll let that be the height of the first rectangle. Second rectangle, between f of 1 and f of 2, we'll choose f of 1 because that's lower, so extend that height over the second subinterval. Third subinterval, between 2 and 3, we see f of 2 is clearly hitting a lower point on the curve than f of 3, so let that be the height of the third rectangle. Fourth rectangle, between f of 3 and f of 4, we see f of 3 is lower than f of 4, so extend all the way to the height of f of 3 and drag that over. Okay, so lowercase s of 4, width times height, 1 times 1, plus 1 times 3, plus 1 times 4, plus 1 times 4.5. Okay, add those together. We get a lower sum of 12.5, which is clearly a smaller value than our upper sum. Okay. Now, some of these problems, I encourage you guys to print this out and work off of the printout page. That way, you don't have to draw all the rectangles. That's part of your homework. I don't think I've printed out all the homework problems, but the ones that are graphed, I think will be easier to work directly off of this printed sheet. All right, that's all I have. Sorry for going over a few minutes. Have a great day. I will see you tomorrow.